Okay, starting chapter 3 with acceleration. Okay, last chapter we talked about velocity, and we said that velocity was a rate of change of position. Change of position over time here. Final position minus initial position divided by time. And that's what we define velocity as. Okay, we use the units meters per second. Okay, it also had a direction. Typically, in a two-dimensional coordinate system, we said to the right or east or up or north was positive, or left or west or down or south were negative, depending on exactly what our coordinate system was. Okay, but what if velocity itself is changing? What happens then? So, first, it's important for us to understand the difference between constant and changing velocity. Okay, what it means to be constant is kind of the opposite of changing. It means not changing, staying the same, staying static. Static is kind of another word for constant. But remember, velocity is a vector quantity. Okay, so vectors have a magnitude and a direction. So if we have a vector quantity, if either its magnitude or its direction is changing, that quantity itself is changing. Okay, so speed was indicative of the magnitude. Direction obviously refers to direction. So if either of those aspects are changing, velocity is not constant. Smaller cursor here. There we go. So if velocity is constant if the object is at rest, it's not moving, it is staying in the same location at all times, or if it is moving in a straight line at a constant speed. In either of those situations, those are all the situations we dealt with last chapter. Velocity was only constant. Okay, and velocity is constant technically if it's if the velocity is 0 as well. But and so this is v is equal to 0 scenario there. If the object is at rest, 0 is a constant velocity. Or if it's moving in a straight line at a constant speed. Now, in either of these situations, since velocity is constant, that means that acceleration is equal to 0. Okay, acceleration is the rate that velocity changes. Acceleration is a changing velocity. If velocity is changing, there must be some non-zero acceleration. 0 acceleration means there is none. There is no change in velocity. Okay, but if there is a change in velocity, then that means the object is either speeding up, first option, slowing down, or changing direction. Okay? You have 1, 2, or 3 options there. Okay? This means getting faster and faster and faster. This obviously means getting slower and slower and slower. You're going from a high rate of speed, a high rate of velocity, to a slow rate of velocity. Or changing direction. Instead of going in a straight line, you are turning. You are zigzagging around. Okay? Any change in direction. All of those would mean a changing velocity and would of course mean that there is some acceleration. In any of these scenarios, the acceleration is not equal to 0. It is above or below 0. It could be a negative number, it could be a positive number. We'll talk about what exactly those ideas mean. So we define acceleration as the rate which velocity changes with time. Super important idea. The rate that velocity changes. If velocity is changing, there is an acceleration. You can't have a constant velocity and some acceleration at the same time. Those are opposing notions. Okay? So acceleration equates to a changing velocity. Kind of get that in your head, okay? The concept of the difference between velocity and acceleration is not a difficult one to understand, but it gets confusing with people because it seems a lot like velocity. It seems like the same thing, but it's really not. Acceleration is changing velocity, speeding up, slowing down, or changing direction. Okay, now if we have what we call a pictorial model, oops, go back a couple slides. We have a pictorial model of different types of motion, okay? These stick figures, like a kind of like what I would call a strobe photograph. Each picture is taken an equal time interval apart, let's just say 1 second. So obviously if we're at rest, we are not moving, okay? If we're not moving, we're going to stay in the same position. Our picture keeps getting taken over and over and over again in the same position. If we're moving with a constant velocity, okay, we are covering the same amount of ground from here to here in each time interval. 1 second goes by, that's how far we went. In the next second, we went an equal amount, another equal amount, another equal amount. Now let's say each of these intervals was 1 meter. 1 meter. Every second that goes by, you're traveling 1 meter. So after the entire time interval, you will have traveled 4 meters. Okay? And again, it's useful to speak of things in terms of intervals again. So 1 meter, 1 meter, 1 meter, 1 meter, okay? The rate, the amount of displacement we're encountering in each time interval, and these time intervals, 1 second, 1 second, 1 second, each of those is 1 second, 1 second, 1 second. In each of those time intervals, we've traveled the same distance. Now over here, if we have a positive acceleration, this means something different. Okay, here's 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Now, did we displace ourselves an equal amount between, say, 1 and 2 seconds, as we did between 4 and 5 seconds? No, not at all. Okay, we went from here to here in that first time interval. In the last time interval, we traveled that much. Okay, you're going at a greater rate. So we want to know at what rate are we increasing our velocity. Okay, acceleration is a rate of a rate. It's a rate of change of velocity. Alternatively, if we're slowing down, that means we have a negative acceleration. You're going very fast. In this first time interval here, we traveled all that distance. And the next time interval, a little bit less distance. A little bit less, and a lot less. We are slowing down. We were going much faster here than we were here. Okay? Both of these are acceleration, are examples of acceleration. Acceleration. So it's kind of important to think of our heads. Think of, we're stopped at a stoplight for this situation. Stopped at a stoplight, turns green. You have to speed up. You're going from a velocity of 0 to a velocity of, 25 miles per hour. Down here, you're approaching a red light. You're approaching a stop sign. You're going at 25 miles per hour, and you're coming down to a stop. Here, you're cruising at a constant 25 miles per hour. No stop signs, nothing in your way in the middle of the road. Okay? As I said, so pretty easy so far. Now, in terms of detecting velocity versus acceleration, there's no difference between being at rest and moving at a constant velocity. Because this is kind of a really important thing in physics. This is actually something that Einstein said was one of his greatest works, is that there is no difference between a constant velocity and being at rest. Think about it. You're driving on a car down the middle of the road. You're going at a constant 50 miles per hour. There's no test you could do inside of that car to prove that you are in fact moving. You don't feel forces. Okay, you throw something up, it lands back in your hand. You drop something, it lands right underneath your hand. There is no universal at rest, okay? Constant velocity and at rest are the same things. So we can't detect a constant velocity. Accelerations, however, are much easier to detect. Think about you're on a long road trip. and you fall asleep in the back seat. One of your friends, your parents, something, they're driving. You're sleeping for a long time. When do you always wake up? You always wake up when you go to pull off the highway. Why? Because you can feel that slowing down. Or, you start to slow down, then you speed up. That's when you always wake up. You can feel that. There's forces acting on you when there's acceleration. But a constant velocity, that's the same thing as riding in bed. If the road was perfectly smooth and you couldn't feel the engine, it, in every physical aspect, would be the exact same thing. Would be the exact same thing as lying at home in bed, totally at rest. But even here sitting on the earth, we're not at rest. We're on the surface of the earth. The earth is, of course, rotating, and we're not at rest there either. Okay, so we'll look at some examples with the motion detector about how exactly we can see velocity versus on your when I get back in school, we can look at the motion detectors at the LabQuest, and we'll show some of the differences between how even the motion detectors can't tell the difference between some types of constant motion versus, just in terms of whether you're moving it or the object in front of it is moving. It can't tell. Okay. Let's see here. So, getting to our equation for acceleration. Super important equation here. Put a star by that. That's going to go on your equation sheet for sure. Acceleration, A, small letter A, is equal to delta V over T. Okay, delta, remember, means change in, Greek letter delta, of course. Every time I do a change in, it's going to be V final minus V initial. The final velocity minus your initial value over time. Okay, so the units for the top are going to be meters per second. The units for the bottom are going to be seconds. So it stands to reason that the units are going to be meters per second, or just written a little bit differently, meters per second squared. That does not mean you square anything in the equation. That is just the unit. It's meters per second getting divided by seconds again. Okay, and again, it is always taken as an average, so don't let that word average figure freak you out. Okay, V final minus V initial over time is always going to be equal to your average velocity. Now, it is a vector quantity as well. That's another big idea. And since it's a vector quantity, it can be positive or negative depending on the direction. Now think about when it would be negative. Think about if you had you were going at 20 meters per second was your final velocity, and your initial velocity was 50 meters per second. You were going really fast. And say you did that in a time of 3 seconds. That'd be a pretty fast acceleration. You went from 20, you went from 50 down to 20. So what's this going to wind up being? Okay, 20 minus 50 is negative 30 over 3. So your acceleration is going to be negative 10 meters per second squared. Okay, that means that you are speeding up at a rate of 10 meters per second every second in the negative direction. Now, the sign of your acceleration does not necessarily tell you which way you're going. The sign of velocity tells you which way you're going. Okay, so really important equation. This is critical to our understanding of what acceleration is. Okay, and remember, we had velocity before. That was the rate of change of position, x final minus x initial over time. And that was for average velocity. Okay, this was average velocity over some time interval. Now, last chapter we talked about the difference between an instantaneous velocity and an average velocity. Notice this velocity does not have any subscript on it. If it did, we would write, AV for average, or AVG, or even a line over it can mean average. But this is an average velocity. What's important over here is these are instantaneous velocities. Okay, this is your velocity at the beginning of this time interval. This is your velocity at the end of that time interval. Okay, v final refers to your velocity at time t. V initial refers to your velocity at t equals 0. Okay, these are not average velocities. This is an average velocity. Two totally different things. Okay, so average velocity, VF and VI are instantaneous velocities. VF corresponds to the end of the time interval. It means what your velocity was at time t. VI is your velocity at the beginning of a time interval. Okay, so if we look in an acceleration table, these can wind up being pretty useful for us. So if we say an object is starting from rest, which means from rest means that VI is equal to 0, and undergoing an acceleration of positive 3 meters per second squared. So we start at t equals 0, and we go through t equals 4. Okay, now look at what our instantaneous velocity is at each of those different points in time. Again, we start at rest, so that's where we get this from. And acceleration says we're gaining 3 meters per second squared, or gaining 3 meters per second every second. So 1 second went by. What is our speed now? 3 meters per second. Another second went by. It's 6 meters per second. Another second went by. We're at 9 meters per second. A fourth second went by. We're at 12 meters per second. We are gaining 3 meters per second every second. It's like saying, I'm giving you $10 a day. After 4 days, how many dollars are you going to have? Well, after 1 day, you have 10. After 2 days, 20. After 3 days, 30. After 4 days, 40. But instead of dollars, we're talking about meters per second of velocity. Okay? Our acceleration was constant the entire time. That's why we were gaining 3 meters per second of velocity every second. Now notice over here, we wouldn't know how to calculate these yet. But notice what's happening to our position. In the first second, we gained 1.5, okay? Since we're speeding up, we are gaining more and more displacement. We are gaining a larger and larger distance or position every time interval that goes by. Okay, so these are our positions after 1 second, after 2 seconds, after 3 seconds, after 4 seconds. After 4 seconds, we traveled all the way at 24 meters. Okay? Now, and again, you don't know how to calculate these yet. We will eventually, but don't worry about that. I just want to show you that, kind of like what that picture is doing. We started off close together. We got progressively further and further apart in each time interval. Now, this last column says displacement per second. This means, this number right here means, okay, this shouldn't even be anything. This is how much you were displaced between 0 to 1 second. This is how much you were displaced between 1 and 2 seconds. This is between 2 and 3 seconds. And this is between 3 and 4 seconds. So this is your displacement per second. Okay, so in that 4th second, you traveled this much. Look at that compared to that 1st second. You only traveled 1.5. But in just that 4th second, you traveled 10.5. Okay? You could see, because we're gaining more distance each time interval, we are speeding up. That's what speeding up means, is that we are gaining more distance in each consecutive time interval. Okay? So these are equal time intervals amounts of displacement. These are just your locations or your positions after each of those seconds. Okay, if we look at another table, okay, scenario is a little bit different now. Object with an initial velocity of 24 meters per second. So we'd say VI is equal to 24. Okay, we don't start from rest this time. And then we undergo an acceleration of -4 meters per second squared. -4 meters per second squared, is that even possible? How do we know that? Yes, that means the exact opposite. That means that we are losing 4 meters per second of velocity every second. Or that means that the rate that our velocity is changing is 4 meters per second every second in the negative direction. Okay? So think about what's happening here. We are initially moving forward. Hold on 1 second. So we have an initial velocity of 24 meters per second. Now, that means that we are moving forward at a rate of 24 meters per second. That's pretty fast. So we're moving along this way, 24 meters per second. Really fast. Okay? After 1 second passes, we've slowed down to 20 meters per second. After 2 seconds, 16. 3 seconds, 12, 8, 4, all the way down to 0. It took us 6 seconds to lose all of our velocity because we are losing 4 meters per second every second because our acceleration was equal to negative 4 meters per second squared. Okay, so losing a lot of velocity. It took us that long to get slowed down and come to a stop there. Okay, our acceleration was constant the entire time. Okay, now we're slowing down, but we're still moving forward. Look what's happening to our position the entire time. Our position goes from 0 to 22 to 40 to 40 to 54 to 64 to 70 to 72. We're moving forward the entire time. So we have a positive position for all of these locations. Positive, 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 positive. Our acceleration is negative the entire time, and our velocity is positive the entire time. We're moving forward, but slowing down. Okay, so a question I always like to ask is, can you have a positive velocity, but a negative acceleration? And yes, of course you can. That means you're moving forward, that means you're moving in the positive direction, but you're slowing down. Okay, so your velocity is pointed in this direction, but your acceleration is pointed in this direction. You're moving this way, but you're accelerating that way. It seems weird because you're not moving backwards, okay, but you are accelerating backwards. So we see the displacement per second. We are still making a positive displacement, okay, just that rate is going down. We're not covering as much ground. In the first time interval, we went 22. In the second time interval, 18, then 14, then 10, then 6, then 2. We're going really, really slow in this last time interval. Now, what if I could magically keep this acceleration up for 2 more seconds? So through a 7th second and an 8th second. And keep this constant acceleration up. So imagine like a cart or something attached to a rubber band. The rubber band's stretching, 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 and it's slowing it down. And then once it slows down and stops it, this is where we're stopped. This is a velocity of equal to 0. The acceleration is going to stop. What's the 7th second going to look like? The 7th second is going to look like we're going, again, we kept negative 4. We are now moving in the negative direction. And the next second after that, we're going to have a velocity in the negative direction of 8. So we're going forward, 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 and then we slow down, stopped, and then start getting flung back in the opposite direction. Okay? So if we look at these last 2 columns, which again, you don't know how to calculate these yet, but if we did, okay, we're going in backwards now. So our positions are going backwards. That's going to be still positive 70. And this is going to be positive 64. Okay, we're going backwards, kind of following the same path as we did before. Okay, and so our displacement per second was negative 2, then negative 6, because we were displaced in that time interval negatively. Went from a higher position, positive 70, to a lower position, positive 64. That's why your displacement here was negative 6. Okay, so this is a little bit trickier scenario where we wound up talking about, where we have a positive acceleration, or excuse me, a positive velocity but a negative acceleration. Totally possible. We could have the exact opposite situation where we have a negative velocity but a positive acceleration. Okay, so this slide's not super important, but just like how we have average velocity and instantaneous velocity, you have average acceleration. We usually are mostly concerned with average acceleration. You also have instantaneous acceleration. Acceleration is often not sustained for very long in real life, so will not remain constant. So just like instantaneous velocity means velocity at some instant in time, acceleration can also exist in that same way. What is our acceleration at some specific point in time? Now, pretty much all situations we deal with are constant or uniform acceleration, which means that we have the exact same acceleration all the time. Okay, we're not going to deal really much at all where the acceleration is changing, because that's like an acceleration of the acceleration, which just gets really complicated. Okay, so in any situation we deal with in which we have constant acceleration, this means that instantaneous is equal to the average at all times. Okay, now constant acceleration means a changing velocity. Don't get those confused. You can't have a constant velocity and some positive acceleration. Okay, constant acceleration means your velocity is changing. So just like we had graphs of motion of position, okay, so we have a position time graph over here, we have a velocity time graph over here. Okay, now we've already talked about position time graphs. On a position time graph, remember that for each second that went by, we had a certain change of position. Okay, 1 over 1, up 10, over 1, up 10, over 1, up 10, over 1, up 10. Okay, so we should know on here by now that our velocity is equal to slope. So for this whole graph, we had a change in position or time. Really just write this out. Our final was 50 meters. Our final position was 50. Our initial position was 0 meters divided by a time of 5. We found our slope, and that gives us our velocity, 10 meters per second. Okay, and that's the slope here, and that makes sense because every 1 second that went by, we went up 10. 1 second, up 10. 1 second, 10. 10 meters for every second. But now we introduce a new type of graph, a velocity time graph, where velocity is your y coordinate and time is your x coordinate. Okay, or it's x coordinate there. So let's think about this, what this graph means and what this graph means. Okay, this graph over here indicates a constant velocity. How do we know that? We know it because the slope is the same thing the whole time. So that's a constant velocity graph. Cool. Now this graph looks almost the same as that graph. Okay. Does that mean that it means the same thing? No, it does not. Let's think about what this graph means right now. 1 second goes by. Now what's on the y-axis is velocity. 1 second went by. At 1 second, we have a velocity of 4 meters per second. After 2 seconds, we have a velocity of 8 meters per second. 3 seconds go by, we're at 12 meters per second. We see the velocity going up. As we go from 0 to 4 seconds, the velocity is increasing. So what is this a graph of? Is this a graph of constant velocity? No, it is not. This is a graph of constant acceleration. Now, how do we know that? We know that because for every 1 second that goes by on our time scale, we have an increase of 4 meters per second on our velocity scale. Another second, another 4 meters per second. Another second, another 4 meters per second. Okay? So this is a constant acceleration. That's what acceleration is, the rate that velocity changes. So whereas this is a constant velocity, this is a constant acceleration. What would constant velocity look like on this graph? Okay, this graph, if we drew this position time graph onto this graph, it would be a horizontal line. Try to make it as good of a horizontal line as I can here. It'd be a horizontal line located at 10. It'd be that line right there. So if we translated this position time graph, it would translate to this on here. See how that means a constant velocity? All 4 seconds are going by, and the velocity is not changing from 10. We're plotting velocity against time now instead of position versus time. Okay, so really, really important idea there, that we understand the difference between these two different types of graphs. Okay, now what if we try to draw this type of graph on here? Okay, this type of graph onto a position time graph, that'll be a lot harder. Okay, if your velocity is going up, okay, velocity on a position time graph is the slope of your graph. So this means that the slope of your position time graph is steadily going up, and it doesn't stop going up. Now, what would that wind up looking like? That wind up looking like a upward curving parabola, constantly getting steeper and steeper and steeper and steeper. But we'll get to that. Okay? We mostly would just want to focus on our velocity time graphs right now. So, we know already slope is equal to rise over run. Okay, we worked on that a lot last chapter. The slope on a position time graph was equal to velocity. But it's also going to be equal to something on our velocity time graph. So again, as we already said, on a position time graph, slope is equal to your average velocity. But on a velocity time graph, your slope is going to equal to your average acceleration. Okay? If we go backwards one slide here, think about what slope would be equal to over here. Your slope is your rise, your change in y. The change in your y value divided by the change in your x value. That's what slope is. But the change in the y value is going to be your change in velocity, because velocity is your y value, right? Then the change in your x value is time. So the change in time, or just time, delta v over t, guess what? That's acceleration. That's the equation I just gave you. Slope on this is acceleration. Up 4 meters for every 1 second we go across. Another second goes by, 4 meters per second. Another second goes by, another 4 meters per second. Another second, another 4 meters per second. Slope on a velocity time graph, super important idea. Both of these, super important. We should already know this, but this is new. Okay, on a velocity time graph. Okay, going between these two different types of graph is gonna get kind of tricky, but we can definitely do it. We're gonna have to do it. Okay, so here's that same velocity time graph again. Slope is equal to rise over run. Rise is the change in y. In this case, y is velocity. So if we look at the whole graph from 0 to 4 seconds, the rise is 16. Okay, the run is your change in time, how much it goes across. Okay, again, we're doing the whole time interval here. The run is 4, so the rise of run is equal to delta v over delta t. That's what acceleration is, right? So our acceleration for this graph is 4 meters per second squared, or 4 meters per second per second. Okay, so here's a position time graph. Let's turn this. It's kind of a weird position time graph, and this couldn't really exist in real life because you can't instantly go from one slope to another slope. But if we look at this here, this has one velocity, this has a different velocity, a different velocity, a different velocity, and a different velocity. Section 1, 2, 3, 4, and 5. Okay, now, if I was to turn this graph into a velocity time graph, what would that turn into? Okay, now if we look over here, okay, these are what our change in positions are. Okay, we can figure out our average velocity here, our average velocity for this interval, our average velocity for here. So for 0 to 1 seconds, our position goes up 8, and our time changes 1, so 8 over 1. So our velocity here is 8 meters per second. In the second time interval, from 1 to 2, we go up 3 over 1, so our velocity is 3. In the third time interval, we go up 7, go over 1. In this time interval, from 3 to 4 seconds, we go down 3 in 1 second. So negative 3 meters per second is our average velocity there. And this last time interval, we go all the way up to positive 10 meters per second. Okay? So this is the average velocity for that interval, average velocity for this interval, average velocity for this interval, and so on and so on. So if we go ahead and turn this into a velocity time graph, velocity over here now, it was position, and now we're turning to velocity. Velocity time graph would be just from here, horizontal line at 8, and then it immediately jumps down to 3. That vertical line, it's not technically vertical, it just, again, this graph isn't really possible in real life, but we immediately go from a velocity of 8, we're looking at the red line now, down to a velocity of 3, up to a velocity of 7, see how that's at 7? Then jumps all the way down to -3, that'd be way down here, below 0, to get into the negatives. And then this one would be all the way up at +10. So we turned our position time graph into a velocity time graph. So, a position time graph. First, what a constant negative velocity would be. Okay, that should be a horizontal line sloping downward. Just kind of imagine in your head what that should look like. It should look like this. That's a constant negative velocity. Remember, we are on a position time graph right now. If we are at rest with a positive position, boom. At rest with a negative position. Okay, see if that makes sense. You guys have questions on these, we'll go back over them when I'm back in school with you here. Letter D says slow constant positive velocity. Slow, so it's going to be not that sloped. So it's going to look like this. A faster constant positive velocity. Same thing, but steeper. We're going to have a higher slope. Now, what about a positive acceleration? Okay, a positive acceleration. Okay, think about what a positive acceleration means. This means that your velocity is steadily getting faster and faster. That means, okay, on this type of graph, slope is your velocity. Velocity is slope. So if our velocity is steadily increasing, that means our slope is steadily increasing. It's getting more and more positive, in other words. So this is one of a couple possibilities, but this would be the first most obvious one. Okay, this yellow line here, it starts not very steep. It's not steep at all. Then it gets steeper and steeper and steeper and steeper. Its slope is increasing at regular intervals. Okay, it's a parabola shape. Alternatively, a negative acceleration on a position time graph, that would be a case in which the slope of the line is steadily getting more and more negative, meaning it maybe starts very, very steep positively and gets less and less steep. So this would be one possibility for a constant negative acceleration. It starts very steep, and then at regular intervals, steadily gets less and less steep, less and less steep, less and less steep, until it's at the very top here, and it has no steepness at all. It's always horizontal. So at that point, the object's like stopped. Okay? Now, almost done. Now, if instead we're looking at velocity time graphs, okay, and we want to draw different types of motion on these velocity time graphs. Letter A, it says a constant negative acceleration. Okay, negative acceleration. That means that we have to have a negative slope. Okay, our velocity is becoming more and more negative. So it has to look like that. A constant positive velocity. Constant positive velocity means that our velocity is not changing. It means the y-axis isn't changing. That means some kind of horizontal line. Constant negative velocity. Same thing, but we are staying at a negative velocity down here. And letter D, a slow constant positive velocity, slow constant positive acceleration. Okay, so we are going to be speeding up. Our velocity is becoming more and more positive. Our line should have a positive slope, but it's slow, so it's not gaining velocity that rapidly. So a nice low slope, constantly increasing velocity. A faster constant positive velocity would mean that we are doing that, but even faster. Same thing, straight line going up, except for steeper. About letter F, at rest. At rest, this sometimes confuses people. At rest, if we're at rest, what is that our velocity? Or what is our velocity? That means that v is equal to 0. So if v is equal to 0 and it's staying at 0, where does the line need to be? It needs to be a horizontal line at 0. you guys can't see that, it's, you know, a line that goes right along the x-axis here and stays there, minus that little weird hump that we did. Okay? So, this stuff's probably a little bit confusing. So, all this is probably a little bit confusing. We'll ask questions when I'm back in the classroom with you guys, or we'll answer questions as soon as I'm back in there with you guys. But just a few things to kind of close out what we're talking about now. Make sure we're here. Okay? We're talking about acceleration and direction of velocity. Talk about the first 10 meters of a race. First 10 meters of a race. We're coming out of blocks. Okay, there's fastest man in the world, Usain Bolt, back in probably 2008 or so. If we're starting from rest. Okay, that means that our final position is greater than our initial position, so delta x is positive. Average velocity has to be positive. Again, we're moving away from the start line, away from our origin, so that makes sense. And we're speeding up, so that means that VF is greater than VI. So delta V also has to be positive because final velocity is larger than our initial velocity. So both average velocity and our acceleration is positive. Okay, moving right along, if instead of the first 10 meters of the race, we're looking at the last 10 meters of the race. What happens after you cross the finish line? After you cross the finish line, you slow down, you celebrate, you win. Okay, so we're still using our starting line as our origin or as a reference point. Now, what about our final position compared to our initial position? That final, okay, our initial position is the finish line. Our final position is 10 meters after it. So as long as your final position is greater than your initial position, displacement has to be positive. If displacement's positive, that means your average velocity is still positive. What about your V final versus your V initial now? So that means that delta V now has to be negative. V final is less than V initial. You're slowing down. Okay, so V final minus V initial, if that's less than, we wind up with a negative number here. If delta V is negative, acceleration has to be negative. So we have a positive velocity, but a negative acceleration. Totally allowed, totally legal, but can be confusing sometimes. Okay? Again, acceleration is a vector quantity. Its direction must be expressed. It's expressed with a positive or a negative. It tells us how velocity is changing, but it doesn't always have to be in the same direction as velocity. If acceleration and the velocity have the same sign, okay, this is the easiest way to remember this. Big star here, big star. Acceleration and velocity have the same sign. We are speeding up. If they have opposite signs, they are slowing down. So this means if they're both positive or if they're both negative, or if it's positive negative or negative positive, we're slowing down. Okay? Easiest way to remember this, okay? This would be, hey, we're going east and we're speeding up east. Okay, if our acceleration is the same direction as our velocity, we're getting faster and faster and faster. If they are opposing each other, that means that your acceleration is taking away from the velocity you have now, regardless of which direction it is. Easy way to remember that here is in this chart. This is the last thing I'll show you today. So if we look at our initial velocity versus our acceleration and what the motion looks like. Start positive, acceleration's positive, we're speeding up. Start going forward, the acceleration's negative, we're slowing down. If you start with a velocity that's negative, with a positive acceleration, you're going to be slowing down. Or if you have negative, negative, you start going, say, west. Well, you're speeding up in the west too, your acceleration's also going to be negative. You're getting faster and faster. You just happen to be going in the negative direction. That's all negatives mean. It just tells you a direction in a two-dimensional coordinate system. If your initial velocity is positive or negative, and you have zero acceleration, your velocity is constant. If your initial velocity is zero, and you have a positive or negative acceleration, that means that you're going to be speeding up from rest in the direction that your acceleration is. So if you have positive acceleration, you're going to be speeding up towards positive. If you have a negative acceleration, you're going to be speeding up towards the negative. Okay, and that's what I'll finish up for now. Bring any questions to class on the following day. It's a lot of information. It can get confusing, so we'll kind of do some review There are going to be, a worksheet or two, some things out of the book to kind of help you along the way. So this stuff does get very confusing, so best for everybody, just kind of stay on top of it.